My name is Viktor Chuvik, and I'm going to introduce the paper titled Exploring Plausible Patches Using Source Code Embeddings in JavaScript. The goal of our paper is to investigate the nature of similarity-based patch correctness approaches. To do so, we trained the Doc2Vec model on an open-source JavaScript project and generated 465 patches for it. These plausible patches, alongside with the developer fix, are then ranked based on their similarity to the original program. We analyzed these similarity lists and found that plain document embeddings may lead to misclassification. It fails to capture nuanced code semantics. What is the motivation behind our paper? Let us consider the user who wants to repair its program using an automated program repair tool. Such tools often generate a vast amount of repair candidates, since generate and validate approaches often validate against an oracle. Such an oracle might be the test suite, so a program is marked as a possible one if it passes all test cases. And of course, there is no guarantee that the generated patch is a correct one. For example, overfitting often occurs. Efforts that have been made to tackle with this problem include patch filtering, test suite expansion, care for patch producing, and many more. Most approaches to date use post-filtering, relying either on test execution traces or make use of some similarity concept measured on the generated patches. Despite the immense popularity of the automated program repair field, the question of patch validation is still open. One possible solution is to use similarity-based approaches. The key motivation here is that if a patch is more similar to the original source code, it might make sense to prioritize this against others. In this work, we use Doc2Vec to create source code embeddings and to measure similarity between code snippets. After a Doc2Vec model is trained, for every code snippet an n-dimensional vector is created on which one can measure similarity. These vectors contain information about the meaning, environment, and context of a word or document. The generated plausible patches then lined up alongside with the developer fix based on the similarities calculated previously. Based on this list, we can analyze which version of the fixed program is the most similar to the original one, the one created by an APR tool or a developer fix. To investigate the benefits of the document embedding approach, we organize our experiment along the following research questions. The first is, how effectively can the similarity-based approach be used to validate plausible patches? So whether it is possible to use document embeddings to filter on or to classify the generated patches as correct or incorrect. And the second is, do correct patches always show great similarity with the original program? Or it is also possible that they are dissimilar to the original program and incorrect patches are more similar to it. And what are source code embeddings? Embedding techniques enable a real representation of text items. So for example, for a source code file, we get a vector which consists of real numbers. For every bug, a small environment of the faulty line was selected, and this was embedded using Doc2Vec. For our training data, we tokenized this small code fragment, separating words and punctuations, except for words with the dot operator. Doc2Vec is a fully connected neural network that uses a single hidden layer to learn document embeddings. The exact configuration of the model can be found in the paper. We evaluated the similarity-based approach on the Enslim project, which is part of the Bugs.js dataset. Bugs.js features a rich interface for accessing the faulty and fixed versions of the programs and executing the corresponding test cases. These features prove to be rather useful for the comparison of automatically generated patches with the ones which were created by developers. On this figure, we can see that for each bug, a number of candidate patches were generated, in total 465. It is apparent that for SLIN 221 and SLIN 323, the number of plausible patches is orders of magnitude more than for any other. This phenomenon might be a good example of weak patch suite, or the fix itself is an easy one. Our main question is whether it is true from the perspective of Doc2Vec that the developer fix lies close to the original program. To measure the quality of the ranking, we used the normalized discounted cumulative gain, where DCG stands for discounted cumulative gain, and IDCG stands for ideal DCG, and P is a particular rank position. DCG measures the usefulness or gain of a document based on its position in the result list, while IDCG basically is the maximum possible DCG value that can be achieved on a ranked list. This is done by sorting all relevant documents in the corpus by their relative relevance. Since the similarity values give us the ordering, each item in the list should have another value which validates its placement. We manually checked each and every generated bug and categorized them based on their relevance. 5 relevance scores were introduced. The first is the score of 3. The developer fixed always has the highest relevance. In ranking, the most favorable is when the patch comes first. The second, if the patch is syntactically matches the developer fixed. We use the term syntactic match when the codes are the same character by character apart from white spaces. A patch gets the relevance score of 1 if it is semantically identical to the developer fix. That is, the two source code have the same semantical meaning, but there may be character differences. It gets the score 0 if we were uncertain about the patch, and -1 if the patch is clearly incorrect. So, for example, there are syntactic errors in it. In addition to these, intermediate categories are also conceivable. On this figure we can see the NDCG metric values. Two developers created the relevance scores on which we calculated the metrics. It is clear that although there are small differences, the opinion of the two developers on patch relevance matched in most cases. We can see that in case of SLIN 217 and SLIN 41, the values are 1.0. This is clearly because the developer fix was ranked to the first place in these cases, and irrelevant documents were placed on the end of the similarity list. The NDCG metric value reached its lowest point and the SLIN 94 bug. Let us examine this from another perspective. If we take a look at the subplot E, we can see that indeed Doc2Vec failed to rank the developer fix at the top of the list. Moreover, more of the patches at the top of the list are incorrect ones, meaning that they hold a low relevance. It is clearly visible that in most cases the developer fix has been placed on a prime location in the similarity list. The developer fix is at the top of the list in 3 cases, while it takes the second place in 4 cases. We also evaluated manually the generated patches. On the figure we can see 2 examples, one from SLIN 1 and the other from SLIN 321. On the top code snippet, the most similar patch were applied, while on the bottom the least similar. Both of these are counter examples. In the first case, the most similar patch to the original one is incorrect, while in the second case, the least similar one is correct. Based on the observed patches, we would recommend a more sophisticated technique to validate patches than plain source code embeddings, because as we have seen, the problem itself is more nuanced and complex than a simple true-false classification. The last item in the similarity list can also be a semantically correct one, even though it is less similar to the original program. From this, we can conclude that while similarity-based methods may be suitable for filtering out too many patches, one should use them for classification cautiously, bearing in mind the possible misclassification. In conclusion, in this work we used Doc2Vec to measure the similarity between generated patches. With the use of document embeddings, we created a similarity list of patches. Similarity-based approach may be useful for patch filtering, although it fails to capture nuanced code semantics. More complex language understanding model may be advantageous in deciding whether a patch is correct or not. Thank you for your attention. If you have any question, I'll be happy to answer them in the QA section.
Okay.
Thank you, Sergey.
Yeah. Hello, everyone, again. We are happy to accept your questions. Please type them in the chat. Okay, we have one question. How you compare it with more traditional patch correctness checking techniques, for example, based on AST-diff?
So how we compared our approach to other traditional patch correctness checking techniques? Well, we didn't compare it because our goal was to investigate whether it is a good approach to measure only similarity between patches and the original source code. So our goal wasn't to say that it is a better approach or to compare it with others. Just the solid basis if it is possible to use such a primitive approach.
But without baselines, it's hard to tell whether this new approach is working or not, right? So maybe it's better to add some baselines to compare against it, and then you can tell, how good it is, how bad it is, right?
Yep, it's true.
Huh?
We have another question. Two fragments of code might have the same embedding. Do you observe this phenomenon? If yes, how would you distinguish them?
No, we didn't observe this phenomenon because the number of candidate patches. Well, of course, it is a lot if you want to observe these patches manually. So if the developer has to check every patch, it's a lot. But to create document embeddings, it's not that much. And on the other hand, we only used unique candidate patches, meaning that there is always a difference between them. I mean, in character differences.
Okay, I have one question from myself. So for now, when you talk about similarity, you talk mostly about syntactic similarity, like based on this embedding. But for example, if you have two variables that may be different, like they have different names, but they're used pretty much in the same way, like for example, I and J. So would your approach still be able to detect this kind of similarity?
Yes, so the similarity can be measured between any code snippet. But the real question is that whether that plausible patch or whether that patch is more similar to the candidate, and whether it makes it a correct fix or not. But yes, using document embeddings, it is possible to measure similarity between any code snippets.
Mm-hmm. We have a couple of more questions. What is the size of your training set? Do you have problems in getting correct patches for JavaScript programs?
We had 465 candidate patches, but we trained the doc2vec model on the whole SDN project. So out of the vocabulary problem shouldn't occur during the embedding phase. And yeah, getting correct patches for JavaScript programs is a whole another story, and it is out of scope of the current paper. But it's a lot different compared to compiled languages, for example, compared to Java or C, because well, of course, because of syntactic differences, and it is also harder to evaluate whether a fix is a plausible one or not, because we cannot just compile the program. We have to run the test cases every time we create a modification on the line.
Mm-hmm. Okay, thank you. And the next question is, how did you retrieve original patches, or that is done manually?
The original patches are in the bugs.js database. It wasn't originally created for automated program repair, but we adapted it, and it has a pretty useful API that can test. So using that, you can actually check out the original code, you can check out the developer fix, and also the test case. You can run the test cases. So it is built in the bugs.js dataset.
Mm-hmm. We have around 40 seconds. Is the plausible patch problem more serious for JavaScript than traditional languages like Java?
I wouldn't say that it is more serious, but I think it is more of a question of a data set and not a programming language. Well, we have to see that the defects4j dataset is pretty suited for the automated program repair field, and yeah, maybe the tools are overfitted for them. So I wouldn't say that it is